Okay, welcome to this third lecture on my course on Markov Partitions and Young towers in dynamical system. The first thing I would like to tell you that the notes change at every class. So I have a new link for today, which is this one. You simply have to change the 2 to 3 comparing to the previous one. And in the next day, there will be a new set of slides. So in the first two classes, we have seen these first two sections in this table of contents. So we have seen, made a brief introduction to physical measures and SRB measures and decay of correlations. And then we have seen these Gibbs-Markov maps, which are useful when we induce given a dynamical system, still for endomorphism, for non-invertible systems. We induce in some region of the phase space, and if the induced map has some good properties, and the good properties are those that define Gibbs-Markov maps, then we have some good measures there, good invariant measures, and they give rise to good measures for the original dynamics. In particular, when we consider smooth dynamical systems and the reference measure for the Gibbs-Markov map being Lebesgue measure, then they give rise to SRB measures or absolutely continuous measures with respect to Lebesgue. Then we use a tower extension to deduce decay of correlations, and we apply that to a family of intermittent maps in two situations, one in the interval map, the other one in the circle map. Essentially, the results are the same, techniques are similar. The only difference is that in second case, we need to induce twice to get the Gibbs-Markov map, but essentially it's the same thing. The good thing of the second one is that it allows us to introduce this solenoid with intermittency today. I'm sorry, I clicked there. It's not very wise to click because it's a clickable link. So today we are going to see this solenoid with intermittency as an application of the results we are going to see. So today, the situation is essentially the same of this second section. So now for maps with contracting directions, for diffeomorphic vertical maps with contracting directions. For that, I'm going to start introducing special sets and with some good structure, and I'll call these structures, I'll call it Young structures. And they have associated to these Young structures, there are a return map or a recurrence time and induced dynamics with associated to the original dynamics. And the idea for those structures is that when you, so they are made of stable and unstable disks. And when you collapse through the stable disks, you obtain for the induced map, you obtain an induced map of the Gibbs-Markov type. And so we will also consider associate to it a tower extension and a quotient of that tower. And using the results from the endomorphism case, we'll be able to deduce decay of correlations in the diffeomorphism case. So let me start introducing these Young structures. So the setting is the following. We have a Riemannian manifold that I'll call M, so highlighting, and F, a diffeomorphism onto the image. We say that the compact set lambda in M has a product structure if the set can be obtained as the intersection of two families of disks, a family of stable disks and a family of unstable disks. And the set is precisely, so you consider the unions of those stable and unstable disks, and the set is precisely the points that are in the intersection. So this is the set having a product structure. So you have here a picture, and there are some conditions for it. Well, the dimensions, the sum of the dimensions is the dimension of the manifold. And each stable and unstable disk, they meet in exactly in one point. So this is kind of product structure for hyperbolic attractors that you know the product structure exists. So given a point, we will use gamma s of that point x to denote the stable disk containing it, and gamma u for the unstable disk containing it. So we'll use holonomies. That's what I introduce here, is these theta transformations. So given two unstable disks, that's what we have here, gamma and gamma prime, we can slide along the stable foliation from one to the other. And so this is what I call theta gamma gamma prime. And we can slide from any point in the set with the product structure to a fixed leaf. Of course, the points intersecting lambda in the same way. So you consider the unstable leaf through that point, and you consider the previous transformation from the unstable leaf to the stable leaf. We say that the set with the product structure, I call it hyperbolic, I think. Well, here appears the word hyperbolic. Well, you can remove it, it's not so important to put it here. Is measurable if the maps are measurable for all leaves gamma and gamma prime. An important concept is this notion that I introduced now, the S subsets and U subsets. We say that the subset of lambda is an S subset if that's the first picture here, if that subset can be obtained by intersection of all leaves, all unstable disks that define lambda, and a subset of stable leaves. That's what we have. So here in blue, we have all leaves that define lambda, and in red, we have a subset of the stable disks that define lambda. So lambda 0 is the intersection points here of the reds and blues. And similarly for U subset. So this is an S subset. A U subset is defined similarly, simply considering a subset of the unstable disks and all stable disks. Okay, so let us now define what I mean by a Young structure. So assume that we have a set lambda with a measurable product structure, and we say that it has a Young structure if the following 5 conditions I'm going to introduce now, if they hold for this set lambda. These conditions appeared originally not necessarily in the way I'm going to present them now. Now it's simplified, so they are simpler than the original ones in the work of Young from '98, the paper in Annals. There are improvements in these conditions carried out by, well, in a paper of mine with Pinheiro, we need to make some simplifications, having in mind some example we would like to apply. And recently, Korepanov, Kozlov, and Melbourne, they also made some simplifications. I will tell you what are some simplifications are merely in terms of the statements. The conditions of Young imply some other conditions, and those that are implied in some sense are simpler than those that Young stated as her conditions. So I think it's better to put the simpler conditions since they are implied by the original ones. But there's a simplification which is actually a strong simplification which deserves to be included here, and I will tell you in a minute what it is. So my first condition is what I call the Markov condition, and it's close to the Markov condition in hyperbolic dynamics. So we say that this Markov property holds if there are pairwise disjoint S subsets of the set lambda. So the S subsets are obtained intersecting S subsets of the stable disks and intersecting with the unstable disks. That's the picture here. And such that these two properties hold. Well, when you consider the union of all subsets, that's what S subsets, they essentially give everything in the unstable disks. I say essentially because this is in terms of the Lebesgue measure, M gamma. I don't know if I said that. I forgot to say that, but M gamma is the Lebesgue measure on the unstable disk gamma, okay? And so this says that when you consider the union of all all S subsets, this gives, and you intersect with any unstable disk, this gives essentially all the points in lambda. And also, it's an important point is that the measure of lambda intersecting gamma is positive. So this is another important property. The second one is I would say the usual Markov property, but not in every iterate of the dynamics, in proper iterates of the dynamics. So for each set, we choose, there is some iterate such that the image under that iterate of that set, so I'm taking S subsets and their images are U subsets. So in the unstable direction, they fill it all. So they fill unstable loops. So that's the tendency when you iterate. The stable has a tendency to contract. That's what happens here to the reds. And the unstable has a tendency to expand. I say the tendency because here is not uniformly hyperbolic dynamics, so it's non-uniformly in the applications. So in the future, this eventually will occur. And so this is the standard condition of Markov property, but the only difference here is that we have this only in the recurrent types, okay? So the stable if, so this happens in a strong sense. The image of an S subset is a U subset in a strong sense, in the sense that the stable leaf goes inside a stable leaf, and an unstable leaf contains the respective unstable leaf. We define the recurrence time and the return map. So this allows us to introduce a return map, since this goes from lambda to lambda. Every lambda I is sent into a subset of lambda. And so we can introduce a return map from lambda to lambda, simply considering on each lambda I the respective power, and also the recurrence time. And we can, similarly to what we have done in the case of Gibbs Markov maps, we can introduce a separation time. So it's the meaning, the smallest n for which they lie in distinct elements of this. This is a mode 0 on leaves, mode 0 partition. So I will refer to this as a partition, okay? So this is the standard definition that we used before. So we can use separation time. So as before, when you consider a power beta, some number between 0 and 1, and beta to S of xy can be interpreted as the distance of the 2 points. Okay, and so this is the first condition. Let's go to the other 4 conditions. The first one is where the big difference to Young presentation of her structures where the big difference appears. Actually, Young considered the condition Y2 for, well, she didn't call it Y, but I call it Y. Condition similar to Y2 is that these stable disks, when iterated forward by the original dynamics, they are contracting uniformly in the future. And in terms of some applications that we have, this is a very strong condition. So, and thinking of what is done, it would be reasonable to consider a weaker form of contraction for the unstable disks. For the stable disk, I'm sorry. So that's what I'm talking about now. And the condition is this one. So we have contraction. See that I'm taking these constants C and beta are uniform constants. We take from in the very beginning. And so, and the condition is that when we return, we have the good contraction. So this is contracting by a uniform constant. And in the middle, this is put here essentially because of systems where we can have singularities, and so in general this is not a big problem. So this is the condition that in the middle we don't expand too much. So the tendency on stable leaves is to contract, so this is not much of a restriction. But we have to put this condition if we want to consider very general systems. That this needs to be it needs to appear as an assumption. Okay, so this is the contraction on stable disks, and we have similar properties for the unstable disks, and we have so this is the expansion on unstable disks. So the expansion is stated as usual in terms of when we go to the image, and when we look back, we have contraction. So that's this condition here. And also similar to the second part of the previous property, we don't, it's not very wild in the middle of the iterates to the return time. Okay, so these are the expansion and contraction on stable and unstable disks. So this is, let me remark that this is only, the contraction and expansion is only at the return times. The third property here in this page is absolute continuity of the stable foliation. That here we have those holonomy maps. We can state it very easily. So saying that given any two unstable disks, we have this holonomy map that I've introduced for sliding along stable disks from one unstable disk to the other. And this condition is saying that the push forward of the Lebesgue measure above is, well, above or below, depends on where you represent the disks gamma and gamma prime, but the push forward of the Lebesgue measure on gamma is absolutely continuous with respect to Lebesgue measure on gamma prime. So this is the usual absolute continuity property, but we need some regularity of these holonomies. This is an important property that we need to impose. And the regularity is this one. So since this push forward is absolutely continuous with respect to Lebesgue measure on the second disk, we can consider the density of this of the push forward with respect to the measure on that leaf, and the density needs to have these good properties. So the first one is, well, is bounded, uniformly bounded from above and below, and the second one is some regularity of the logarithm of the density. And this is a kind of, as before in the whole the Gibbs-Markov situation, when we consider the Jacobian, well, Jacobians are related to these densities. When you consider the Jacobians, if you think of this as being the distance, the beta to the separation time, so we are imposing some type of Holder condition to the Jacobian. Here to the density of the push forward with respect to the measure on the leaf. So this is the absolute continuity property. And there is also, yeah.
Payman asked a question. He wants to know if the distance that you consider is this distance on the leaf.
Yes, it's always the distance on the leaf. Yes.
Okay, thank you.
Even though in application it doesn't make much difference, because the curvature of those disks is very regular, and so it's essentially the disk. I'm sorry, here, no. Here, the distance is the distance in the manifold. But as I said, in terms of applications, these disks are very regular in terms of a curvature. And so it's not important if it's the distance in the manifold or in the disks.
Actually, you make no assumption on the curvature of these stable and unstable disks?
Yes, there's no assumption here.
Okay.
Of course, when we build them, we need some control on curvatures, for otherwise we don't have these properties. So in principle, I don't need this, but in practice, then I will obtain situations where it's in the disk is the same. Okay. So, and the third one is the regularity of the Jacobian. So this is the Jacobian of the return. So the return map goes from one unstable leaf to other unstable leaf. And so here we are considering, is from the very beginning, we are considering smooth maps. So this Jacobian exists. And so Tx here is the tangent space at that unstable disk. And so comparing the logarithm of the Jacobian at 2 points, we have this property. So again, it's a kind of a holder condition type, okay? So this is the regularity we need for the Jacobian of the return map. As we had before in the Gibbs-Markov situation. So this is parallel. The only thing that we didn't have there was the contrast. So Y2, it makes no sense in that case. And Y4 also makes no sense because in the Gibbs-Markov situation, we don't have stable leaves. The other properties are similar. Okay, so we say that the Young structure has integrable recurrence times if the integral of the recurrence time for some, and by this absolute continuity property, then necessarily for all, we have this integrability condition. In many cases, this is not asked in the definition. In many cases, the unstable disks are totally contained in lambda. This is the case, for instance, when we apply to partially hyperbolic attractors. This is not the case in the construction of Young and Benedicts and Young for Hannon attractor. They didn't obtain the property of the disks contained in the Young structure, lambda. Of course, the disks are contained in the Hannon attractor, but the Young structure is a subset of the Hannon attractor. In such case, this is just for one of the results I want to talk for an application I have in mind. I will refer to this as a full Young structure. So full Young structure means the disks that define the Young structure, the unstable disks, they are contained in the Young structure, in the set with the Young structure. Okay, so a first result. So,
can I make another question?
Yeah, of course.
So is this Y5 property a sort of bounded distortion just for the return times?
Yes, it's bounded distortion. Yeah.
Okay.
Well, usually I call it Gibbs. Well, first because Gibbs property is close to this for this special observable log of the Jacobian. I usually call bounded distortion for iterates. When you iterate and in the forward iterates, and you usually have that property. So when I consider iterates by the return time, and so I will refer to that as bounded distortion. But of course, this is a bounded distortion property in that sense.
Thanks.
Okay, well, since the first case for endomorphism, I called it Gibbs-Markov, I would like to stress something related to Gibbs, and what is related to Gibbs is the bounded distortion property. So now I will state several results which are parallel to results we obtained in the endomorphism situation. So the first one is for the return map. For the return map, if we have a set with a Young structure and we have the corresponding return map, then it has a unique ergodic SRB measure. By SRB measure here, I mean simply a measure. So the return map is for the Young structure, we have the unstable disks, the stable disks, that geometric, very regular picture. And so SRB measure means a measure that lives on lambda, and the conditionals on the unstable disks are absolutely continuous with respect to the conditionals of the Lebesgue measure. Okay, so it makes sense. Formally, I introduced SRB measure for smooth dynamical system. This FR is not smooth, but there is a smooth structure behind it to define it. And so we can talk about the continuity, the absolute continuity of the conditionals in those unstable leaves. Moreover, the densities of the conditionals of this SRB measure they are, of course, by definition, they are absolutely continuous, but more than that, the densities are bounded from above and below by constants. Well, the situation is, as I said, similar to the situation we had before without stable directions. And the fact is that for the induced map, we have uniform estimates of expansion in this case. And so this leads to very regular properties of the densities. And the proof is similar to theorem 2.5 is the theorem that says that when we have an induced Gibbs-Markov, then the Gibbs-Markov map has an absolutely continuous invariant probability measure. And if you remember in that case, I didn't give you the details, but I said you consider the Lebesgue measure, you consider the push forwards by the Gibbs-Markov map, and you consider the time averages and you have a sequence of measures, and then you consider weak star accumulation points and you control the densities of these. Here is the same situation. The only difference is that you start with Lebesgue measure on an unstable disk, and then you consider the push forwards by the return times, by the return map, and you consider you also can, since the return map is uniformly expanding, you can control the densities of these measures, and you obtain uniform bounds from above and below. And so a weak star accumulation point will be the SRB measure. And again, since we have a unique ergodic SRB measure for the induced return map, then we can push it to the original dynamics. So if F as a Young structure with integrable recurrence time, and here the integrability as before is important, then F as a unique SRB measure. Of course, again, if we cannot stop here in the part I highlighted, is the unique that intersects that Young structure. Of course, the system can have other region which does not interact with it, and so there's the possibility of having other ergodic SRB measures. But giving positive weight to the Young structure, the set with the Young structure is unique as before. And again, it's obtained with this formula. So you can see the push forwards, the measure for the induced system restricted to the set of points which return after time j, and then you consider this sum. So it's exactly the same formula. And the full Young structure appears here because of applications I'm going to give you on the next lecture. If the set has a full Young structure, and the full Young structure is contained in some compact transitive set, then the support of mu coincides with this compact transitive set. Now, the idea is simple because the measure contains disks if it's a full Young structure, the measure contains disks in the support, and then you iterate unstable disks, and then you iterate these unstable disks, and by transitivity, it gives that the support of the measure necessarily is the whole set omega. These omegas in practice will be attractors for the dynamics, transitive attractors. Okay, so this is the only point today I need this full Young structure. So I recall that full Young structure means the unstable disks that define lambda, they are contained in lambda. So you can see proofs. Well, they are similar, of course. Technically are somewhat more involving than in the previous situation of Gibbs-Markov map, but the ideas are the same. Okay, so decay of correlations. So inducing schemes are important to obtain SRB measures. It was in the case of endomorphisms, and now in the case of diffeomorphisms. And merely using the inducing scheme, we don't need that in tower construction are useful for other purposes. For obtaining the SRB measures, it's important. The only important thing is to have this induced map with the good properties. So decay of correlation. So this is what I would like to tell you today, is to give you an idea of the proof of this first theorem here. So what is the content of it? So assume that we have F as a Young structure with integrable recurrence time. Well, if this holds, then it has a unique ergodic SRB measure intersecting the set. So this is the contents of the last theorem. Well, and if the greatest common divisor of the recurrence times is 1, then we obtain the same conclusions that we have in the endomorphism case. So the decay of correlations is polynomial with respect to that measure if the recurrence times decay polynomially fast. And the decay of correlation is stretched or exponential, if the recurrence times decay stretched exponential or exponential. Okay, so this is exactly as in the previous situation. And as in the previous situation, we also have a result for the case that the greatest common divisor is not 1. And as before, the proof is very similar. So as before, we can decompose the unique, so mu is the unique ergodic SRB measure given positive mass to the set lambda. And so we can decompose into a finite number of exact measures, and mu is precisely the mean of those measures. And one measure is the push forward, there's a cycle, one measure is the push forward of the other one. And we have the decay of correlations for the respective power. And as before, the number of measures can be strictly smaller than the greatest common divisor. Well, as before, here to obtain this Young theorem on decay of correlations, again, we will use a tower construction. And again, we'll have a semi-conjugacy from the tower to the original tower system to the original system. And that semi-conjugacy is not necessarily 1-to-1, and so it's not a conjugacy. And so it may happen that 2 measures in the tower give rise to only 1 in the original system. And for that reason, that's the reason why we can have less measures than the greatest common divisor. So, and the conclusions are similar. So for those measures, we have the decay of correlations, and with the same rates, polynomial or stretch exponential. Okay, so the idea now is to prove a theorem, to give you an idea. Proving, I would need more than 4 lectures, but to give you an idea of the proof of this theorem. Okay, so as I said, it uses a tower construction, and the tower is introduced exactly in the same way as before. Since we have the induced map and the recurrence time R, you can introduce. So this is the same expression. Well, I'm using different notation. So here I'm using hats. This is because I'm going to consider a quotient. So see that lambda, the points in lambda, through the points in lambda, there are stable and unstable disks. And so there are points in lambda belonging to the stable or unstable disk of another point in lambda. In particular, there are points in lambda belonging to a stable disk of another point in lambda. And we'll make a quotient through stable disks. And for that quotient map, for the return map, has some good properties. It will be a Gibbs-Markov map. And for that, I will consider a tower, which is of the type introduced in the previous lecture. And for that tower, I won't use the hat. So essentially here, the novelty is the notation. It's defined exactly in the same way. We introduce the tower, goes up to 1 unit before the recurrence time, and then the dynamics in the tower, the levels. And we have a natural partition in the 0 level, because the 0 level is identified with lambda in this case. And we have there the natural partition of the lambda i's. And so we can push that partition in the 0 level to partitions in the higher levels. And we obtain a global partition of the whole tower. I would call this global partition Q hat. And again, we define exactly the same projection from the tower to the ambient manifold. This is the same map, or defined in the same way as before. And again, for the same reasons, we have that it's a semi-conjugacy. between this tower and the original dynamics. And this tower also has some good properties. It has a unique ergodic SRB measure, new hat. And this ergodic SRB measure, the projection or the push forward under this pi here is precisely the unique ergodic SRB measure for the original system, for which such that gives positive weight to the set lambda. So we have, as I said, we have with the return map, we can construct the SRB measure of the original system. With the tower, we can also construct an SRB measure and they coincide. So the idea is that the projection gives the measure that we constructed before. And this is one of the good things of this tower is that it's the SRB measure is a projection. So we have a semi-conjugacy of the system. So it's not only this property, but also the projection of the good measure in the tower is a good measure in the original dynamics. Okay, this is again parallel to what we had before in the endomorphism case. So the novelty appears here. So this allows, so we have the return map, and we can introduce a quotient map of the return map. So recall that the return map is defined for the points in intersections of unstable disks with the stable disks. So I've put, so I'm going to define a quotient associated to a fixed unstable disk. So I fix an unstable disk, and I take a point in the intersection of that unstable disk with lambda, and it has an image, and that image belongs to some other unstable disk. And so the image is FR of that point, and then we slide through the stable leaf through this point, FR of X, and we obtain a point in the original leaf gamma 0. Okay, so this is what I'm going to call F. So this is the quotient of the map FR. Okay, so recall that theta gamma 0 is projecting to the leaf gamma 0 or disk gamma 0. Well, and this map, having in mind all properties that we have put for the set with the Young structure, is not difficult to believe that this map is a Gibbs Markov map. With respect to the reference measure is naturally the Lebesgue measure on the disk, and the partition. So for a Gibbs Markov map, we have a reference measure and a natural partition for that map. And with respect to the good partition, what is the good partition? Is intersecting gamma 0 with the elements of the partition associated to the Young structure lambda. Okay, so it's not difficult to prove this result. It follows from the properties that we have imposed to the Young structure. And this projection is actually, well, this is essentially because FR sends stable disks into stable disks by the first property, the Markov property in the Young structure. We have that this the transformation theta 0, so theta gamma 0 is the projection to the unstable disk gamma 0 is a semi-conjugacy between this new quotient return map and the return map that we have. And this is a very important property. And it happens that if nu is the SRB measure for FR, then the projected, so the push forward of nu through this projection map, which is the holonomy, is the F invariant probability measure such. See that since F is Gibbs Markov map, by the results we have seen in the last days, it has a unique invariant probability measure, which is absolutely continuous with respect to the reference measure, which is Lebesgue here. And that is precisely the push forward under this projection of the good SRB measure for the return map. So we have this very good relation between the measures that we construct using different methods. Okay, so we have this Gibbs Markov map. We can associate to it, as I said, we can associate to it a tower as the one constructed in the second lecture. So consider the quotient map and consider the tower map with the recurrence times, which are the recurrence times associated to the return map. Notice that the recurrence times for this map are precisely the restrictions of the recurrence times that we had in the beginning, and I called it RIs. And notice that the levels of this tower are contained in the levels, in the respective levels of the tower with the stable directions embedded in the structure. This is because we made the quotient of stable leaf. So what remains is an unstable leaf, and is contained in the respective unstable leaf. And so, the tower is constructed in a similar way. So this happens. And it also happens that T is the restriction of T hat to delta. And moreover, we also have a natural projection. So it is given by the projection from one tower to the other, is given by the projection that we had before from the set lambda to the lambda intersection with the gamma 0. And so see, the towers are essentially in higher levels copies of lambda. And so what we are doing here is in the second coordinate, we don't do anything. Second coordinate is the L here. In the first one, we simply collapse to the leaf gamma 0. And that's it. And it's very natural to see, it's very natural to obtain this semi-conjugacy property. And moreover, one more relation which is important. If nu hat is the ergodic, we have seen that nu hat, so T hat, so the tower T hat has an ergodic SRB measure, which are called nu hat, then the projection through the push forward under this theta transformation is the unique ergodic T invariant probability measure, which is absolutely continuous with respect to M gamma 0. Well, is the one that we obtained in our second lecture. Okay, so there's, as I said, there's all the possible good relations they hold. So these projections always project the good measures in one C. So we have several dynamical C. So we have the original one, we have FR, then we have the quotient, and we have the two towers associated to the FR and associated to the quotient, which are called capital F here. And we have natural projections, the thetas, and the pi, and all the good measures, the SRB measures, they project under the projections to the good SRB measure. This is key feature that will help us. Okay, so as I said, I'm trying to give you an idea of the proof of the decay of correlations of Young theorem in this situation. So let me recall some of the things that we have, making the point of the situation. So we have this semi-conjugacy between the tower and the original dynamics here with stable directions. We have this semi-conjugacy between the two towers, and given H stands for the set of Holder continuous maps defined in a manifold. So we can consider so maybe we can look at this picture here. So given a phi here, we can consider the composition of phi with pi. And so we have an observable in this tower hat. So that's what I call phi hat, psi hat, and similar for phi hat. Okay, so we have a unique SRB measure for T hat. We have a unique SRB measure for the original dynamics intersecting the set with the Young structure, and we have a unique SRB measure or absolutely continuous with respect to the Lebesgue measure of that tower, the tower there, the quotient tower. Well, by the results that we have just told you, we have this relation here. Well, by one of the exercises, if we have this situation, then the decay of, whenever we have The exercise is whenever we have a semi-conjugacy. So the exercise was stated in the endomorphism case, but there's nothing specific of the endomorphism. So whenever we have a semi-conjugacy and such that the measures are projected, so the projection of this measure hat is the other one, then we have the correlation term is exactly the same. So see that phi hat and psi hat are precisely the composition with the semi-conjugacy. Okay, so this is exactly the exercise. And so we want to obtain estimates for this decay, the decay of correlations with respect of f with respect to the measure mu. And so we pass the problem to this tower hat. So it's not the quotient tower, to this one. This is the one which is semi-conjugated to the original dynamics. So it's the one that is an extension of the original dynamics. So it's enough to obtain estimates for the tower system. The idea here is to reduce to a problem on the quotient tower. And you could say, well, maybe this is easy because we have also a semi-conjugacy between the tower and the quotient tower. We use what we already know for the quotient tower, previous lecture, and deduce it for the new tower, and so for the original system. The problem, look at this picture, the problem in this picture, well, there's a big mess here. The problem is the picture is that the arrows here, this arrow, oops, I cannot, this has some problems, this is one. So this semi-conjugacy here goes from the tower hat to the tower without hat, so this goes in the wrong direction. So this means that we could deduce the decay of correlation of T knowing the decay of correlation. So this is to say that T hat is an extension of T. The dynamics is an extension of T with the measure nu hat is an extension of the T hat with nu hat is an extension of T with nu. So this goes in the wrong direction. Nevertheless, we can manage to bring the information from T to T hat, okay? So this is the idea of what comes next. So it's not trivial, but still doable. So that's my next goal is to give you an idea of the proof of this. So we are going to reduce the problem that we have here. So we now want to compute this correlation term, which is highlighted here. And so I'm going to reduce it in a certain way to a problem in the quotient tower. Well, first of all, I'm going to take an arbitrary n. So n is the n that appears there. And I'm going to take k of order n over 4. And I'm going to consider the refinements. So we have this tower T hat. We have the partition in the tower, the natural partition. And I'm going to consider the dynamical refinements of this partition. So that's what I call, until the iterate k. So that's what I call q hat k. And I'm going to consider a discretization. So we have this, this observable phi hat. And also, I will also consider for psi hat. So I just tell you what to do for a generic phi hat. And so it will also be defined for psi hat. Let me recall that phi and psi here, they don't have exactly the same roles. So it's not symmetric, the roles. But for this definition, it's no problem. So how do we define? So we consider an element in this refinement of order 2k. See that I'm taking 2k, the refinement of order 2k, and I define restricted to the element in that refinement 2k. I consider the infimum. So we consider the kth images of points in Q, and we evaluate phi hat on that. And then we take the infimum overall points when X ranges in Q. So this phi hat, this map phi k, this map is constant. by definition, in the elements of Q. And Q belongs to the 2K refinement of the original partition. See that the elements, the partitions, these dynamical partitions, they are dynamical partitions obtained by the dynamics in the tower. The tower, the partitions, the tower makes no partition in stable leaf. So we can think of this function also as being defined in the quotient, in the domain of the quotient tower, because the infimum is constant. It does not depend on the leaf. So, well, so let's start the reduction of the problem. This first proposition, well, this is a straightforward calculation. It takes 1 or 2 pages, but it has no significant ideas behind it, and just a straightforward calculation. We can prove the following. So this is the correlation with respect to the tower hat is what we want to estimate. And we can prove that it's bounded by the correlation with respect to the quotient tower. Well, that's good. And the good measure there. Well, we pay a price. Is not anymore this the same observables, is this phi k and psi k. Okay, but they are discretizations. See that these domains, when we iterate, so when you consider the refinements of the partition, they are smaller and smaller. So the discretization is close to the observable itself. So it's not a big difference. And then it appears here too, well, appears the zero norm, since we are taking phi and psi, both hold a continuous, then the zero norm is finite. So this is the sup norm. And we obtain 2 L1 norm terms. So L1 norm here is with respect to the probability measure in the tower. Okay, so, and essentially is psi hat evaluated on the K image minus the psi hat. So this is the idea is that this will be small, and it's not hard to believe that, since look at the definition of phi hat or psi hat. So when you iterate a lot, then see that we are taking iterates much higher than the iterate much higher, well, it's double than the iterates we take here. So it's still there's some refinement there, and so we can control this L1 norm term. So we have 3 terms that we need to control now. This correlation term and the L1 norm term. So that's the way I will refer to them. So we first consider the correlation term. And this is the point where we are going to reduce the problem to a problem in the tower, the quotient tower. Well, suppose that phi k is not 0. Well, if phi k is 0, then the correlation term, there's nothing to be done because the correlation term is 0. So see, by definition of the correlation term, whenever the observable phi is 0, then the correlation term is 0. So nothing has to be done. So we can assume that phi k is not 0, not equally 0. And we consider this phi k star. What was phi k star? This has been introduced in the previous day. Phi k star is a step towards passing observables in the original dynamics, in the non-invertible case, to observables in a certain family of the tower associated to that system. Essentially is adding a constant to this case, to phi k. So how do we observe it? Well, how do we construct it? We add a constant in such a way that phi k becomes strictly positive, and then we divide by the integral with respect to the measure nu, in order that it has integral 1. Okay, so that's what I'm not going to show you what is in 11, because then I will take a lot of time to get to this point here. But if you go there, is essentially what we did. And then we consider the probability measure. I call it lambda k, probability measure whose density with respect to the good measure in the quotient tower is precisely this function here. Well, it follows. Well, I introduced this this new function star precisely to obtain this result. That's the content of this lemma 220. So we have seen that we can reduce the correlation problem in that case, but the objects are exactly the same, to a problem on the way the push forwards of this initial density are approaching, on the speed at which they are approaching the invariant measure for the tower. So this term here is precisely the total variation of this sign measure, which is the difference of the two. Okay, well, you could tell me, well, now simply show that, so simply apply that what we had, because we made some estimates on these terms. There's a theorem saying that if this term, I'm highlighting here, decays polynomially fast, then the decay of correlations is polynomial, exponentially fast, exponential, blah, blah. The problem is that this function, the density, which I call of lambda k star, is not sufficiently regular. So the density is precisely phi k star, is not sufficiently regular. So we need to make it more regular. And for that, we are going to iterate under the tower system 2k times. The idea is that as for uniformly hyperbolic dynamics, iterating densities, transfer operators and things like that, iterating densities, provided they lie in the good spaces, they become more regular. And here is the same. So I consider that measure whose density, if I try to estimate, is not sufficiently regular. And sufficiently regular is to lie in the space associated to this lemma 220. And the space I'm going to highlight it now is the good space for the observables in the quotient tower. So consider a sufficiently good number of iterations or push forwards of this measure, and then consider the density of this new measure. So see that there was a star before, now I get rid of the star iterating under T2k star. And now, and phi is the density. So see that I have this by definition, and this is this, and this is this. Where rho is the density of the invariant measure with respect to the reference measure. Well, since it's easy to see from what I've defined before, I'm not going to check in details, but we can easily see that this is true. And so the important thing now is to see that, let me just, and this here. So the important thing is that with this, we reduce the problem above on correlation to this problem here. And now, as I said, this lambda k has a density which is good. So there is some C such that phi k is precisely the density. So that's what I call the density, I called it phi k. Phi k lies in the good space, and there's a uniform, see that there's a uniform control, as I said, in the result where I've given you so now it's not here anymore, so now it's here. So there is a result saying that if the recurrence time decays polynomially fast, then this decays polynomially fast. If the recurrence time decays exponentially fast, then this decays exponentially fast. And I observed in the end of that result that the constants in the conclusion, they only depend on bounds for the constant associated to the observables. And I observed that, well, if you go there to the theorem, the observation is that it only depends on these constants, and in fact on upper bounds for these constants. And since we can prove that we have this uniform upper bound, then we can prove. Now notice that k is of order, I've chosen it, of order n over 4. So n minus 2k is of order n over 2, so is of order n, okay? So we can apply that result and obtain the good estimates for this quantity here. So the drama could be in the result there are, in the conclusions there are constants which depend on the constants depend on the observable. The problem could be the constants for which we bound this total variation here. The constants could depend on k. That would be a big problem, but they do not depend. So that's the message, because we have this uniform bound for this. So this is the constants associated to the functions in this space. Okay, that the notation I used. And so this is the way we control the correlation term in this proposition. So let me now give you a brief idea on how to control the L1 norm terms. So let me recall what. So these are the L1 norm terms here. This one and this one here. So they are of the same type. So the functions phi and psi, they are Holder continuous functions. And Holder continuity plays an important role at this level. And so we are going to control those L1 terms. So given a point in the tower, let bk of that point be the number of times that up to time k, the point returns to the base level, to the 0 level. Okay, so bk is the number of times it goes down to the 0 level. The idea is that going down is good, because when we go down through a hyperbolic map where we have contraction in the stable, uniform contraction, the stable leaves uniform expansion in the stable leaves for the return to the base. So we are going to put some estimates in terms depending on the number of visits to the 0 level. Well, see that if we take any 2 points in an element of the 2k refinement or dynamical partition, then we have, by definition, because the points have the same itineraries, up to 2k. After 2k, we don't know. But since we refine 2k times, if we consider points in that refinement, if you consider until iterate k, they always visit the same elements in the partition. And so we have this, and in particular, this is what matters in partition bk of y is equal to bk of x. And so if we take a point in an element of the partition, so I've given 2 points. So the idea is that there is a point. So we have this product structure. So given a point in that element, there is a point such that the intersection of the stable disk of one point with the unstable disk of the other is another point in that partition. So this is according to the way we have defined this object. So this is the local product structure. So we can control the distance. This distance, as you will see, this distance will be natural. And why is it natural? So let's look. So we want to control these terms here down, because integrating this with respect to nu hat, we obtain precisely the L1 norm we want to estimate. And see that what is phi hat? Well, phi hat is precisely phi composed with pi. And so we have here is phi composed with pi composed with this t hat k. And so we use the fact that phi is Holder continuous. And here you say, well, but here you have phi k. But phi k, according to the how we have defined it, is still something of this type, because we have defined precisely as the minimum over all points x in Q, according to what we have here. So phi k is of x is again phi hat t hat k of some y. Okay, and so using the fact that phi is Holder, we pass this to estimate this distance here above. Okay, so essentially only using the the definitions of these objects phi k and phi hat. And so this distance is bounded by the triangle inequality. So we can compare the distance of these 2 points. So it's the same type of distance, but now with x and z. And x and z, they belong in the same unstable disk. And z and y, they belong in the same stable disk. And the idea is to control this difference here using the fact that we know that they have any 2 points, so bky and bkx, they are equal. And so we can control, so every time, so the idea is that every time we come to the ground level, we have expansion in the unstable direction and contraction in the is the other way around. We have expansion in the unstable direction and contraction in the stable direction. And so we can control this by this quantity here. Is essential. So sigma is the rate of, essentially is the rate of expansion and contraction. Okay, so we can control that, essentially estimated the number of visits. And then we have that, well, since bk is constant and stable on stable disks, we can easily see that integrating. So we want to estimate the L1 norm. We want to integrate this with respect to nu hat, or now using this estimate, integrating this with respect to the nu hat. Well, we have here, why do we have here this tk term? Is because of the unstable direction, because the contraction is put in terms of the images under. So we need to take tk iterates, and so is the contraction is stated in terms of the images, and so that's why this appears here. But this is not a problem, because we are going to integrate with respect to a measure nu hat, which is invariant with respect to t hat. So integrating, so we divide the integral into 2 integrals, and they are equal because we are integrated with respect to composition with the dynamics for which the measure is invariant. And this is to say that integrating with respect to nu hat is the same of integrating with respect to nu, because these bk, according to the way we defined, they are constant on stable disks. And so since the measure is, one measure is the projected through the holonomy on stable disks to the other one, we obtain this. And the last estimate is obtained. Well, for that, I need to introduce this. So see that this is the sequence of recurrence times. So see that f here is the quotient dynamic. So I'm considering the first recurrence time, and then I consider the image through the quotient dynamics, or through the return map, and then I consider the next one. So this is the sequence of consecutive, for a point of consecutive return times. And we can, so as I told you, we need to estimate this integral, and we can estimate this integral in terms of these measures here, and it takes in particular into account this RL here, and the point now. So this is somewhat involving calculation, and so we obtain this, and so we have passed the problem on the L1 norm to this thing here, and it's not difficult to see that in the polynomial case, we obtain a polynomial estimate losing 1 unit. Even though we have here RL, it's no problem. We can obtain a polynomial estimate losing 1 unit in the exponent of the polynomial rate. And in the exponential and exponential cases, we don't obtain, we don't lose anything. So this is clear in the first term here. In the first term, of course, if it's exponential, then the tail of the series is still exponential. For the other one, it's not so clear, but it still can be proved. And so this is the way we obtain the control on the L1 norm terms. So now for this lecture, I finish with an example of application of these results. And in the next day, I plan to obtain some more applications to partially hyperbolic systems. So here I will give you a simple example where we can see some of the ingredients that appear in the general situation of partially hyperbolic systems. But here is easier to handle because the dynamics is very well known. And what is this? So the dynamics is what I call a solenoid with intermittency. So this is due to my this appeared in a paper by myself in Pinheiro in 2008, where what is the dynamics? We essentially go to the solenoid map, which I introduced in the very beginning of these lectures. So the solenoid map, I describe it as a skew product in S1 times disk. And in the S1 direction, I took 2x mod 1. Well, we can take any expanding map in the S1 direction. And in the disk direction is a uniform contraction. And so in this way, we obtain the usual solenoid map. Is a diffeomorphism from the solid torus into the image. And this new system is essentially you go to the solenoid map and you replace. So the idea is to replace in the dynamics in the base. So we can think of the solid torus as a product and the solenoid as a skew product in this product system. And we replace the expanding map by one of those maps that I consider the intermittent circle map. So for instance, go to 2x mod 1 and in the fixed point, you make it tangent to the diagonal. Okay, so this is the intermittent circle map, and we obtain some results for this intermittent circle maps. So this is what I call solenoid with intermittency. So the intermittency appears in the base dynamics, thinking of the solenoid map as a skew product. See that for that map, intermittent circle map, we have seen that it is, so I cannot highlight this part here, I don't know why, but no problem. So it appears, so actually it's a family of maps that we introduced with some exponent alpha. And we have seen that if alpha is between 0 and 1, then the map, the little f, and then the capital F now, the map is only C1 plus alpha. If alpha is smaller than 1, it's not C2. If alpha is greater or equal to 1, then the map is C2. So the result is exactly the same as for the base dynamic. But before the result, let me say that this solenoid maps again has an attractor that I call omega, and is obtained precisely computing. So M here is the solid torus. So is obtaining intersection of the forward images of the solid torus. And so geometrically is the same picture. So the solenoid. So when you cut, you obtain a counter set of lines passing through the points. It's easy to see that we have a fixed point for the base dynamics corresponding to the 0. And so since we have contract, so the fixed point gives rise to a fixed disk in the solid torus, and it's a contraction, so there is a fixed point there, and in fact it is unique. So let me consider this point. I call it P0. We can compute this fixed point, and well, this is for 2x mod 1, and then we can see that well, due to the direction in S1, the little f as derivative 1, so it has an eigenvalue 1. So this omega is not a hyperbolic set. Okay, so this is just to be sure that we are not reproducing results that we already know in the hyperbolic setting. Okay, well, and the conclusions are exactly the same that we had for the intermittent map in the circle. So if if alpha is greater or equal to 1, then the Dirac measure now at this point here is a physical measure, and its Bayesian covers almost all the solid torus. M here is the Lebesgue measure in the solid torus. So that's the situation for which the physical measure is. It's very simple, it's the Dirac measure. If so, this for alpha greater or equal to 1. For alpha smaller than 1, again, as in the previous situation of the circle map, the dynamics has a unique SRB measure, ergodic SRB measure mu. Moreover, it is exact. The support coincides with the whole attractor, and the Bayesian of this SRB measure, which is a physical measure, contains the solid torus almost every point in the solid torus. And moreover, the decay of correlations is of this order. So this is the same estimate, so the same type of conclusion that we had in the circle. So the idea is to, again, to induce, now obtaining a set with a Young structure, but the recurrence times will have exactly the same estimates that of the base dynamics little f. And so you have the same estimates that we had before, and so that's why it yields this decay of correlations. Okay, so that's the idea of what comes next. So to induce and deduce. Here we have a semi-conjugacy between the circle dynamics and the torus dynamics. So the circle dynamics little f and capital F, which is the projection of the first coordinate. It's very easy to see that, well, it's a skew product, so this happens. And so we have this. Let me give you a brief, I'll give you the proof of the second item. The second item is the simple one. So we already know that the Dirac measure is the physical measure for the base dynamics. And the Bayesian, as we have seen in the previous situation, is almost, so M1 here is the Lebesgue measure in the circle map. And so the Bayesian covers almost all S1. So this is what we have seen. Well, it follows that the pre-image by the projection of a full measure set in the circle necessarily has full measure now with the Lebesgue measure in the solid torus. Well, this is because the projection is the projection along the disks, which are very regular, and so we obtain this full measure. So given any point here, so this is the point such that the projection, we know it falls into B, and B is the set of points for which you know the push forwards weak star accumulation points are converging to the Dirac measure on delta 0. So we take a point in the pre-image and consider also the set, these push forward measures of the Dirac measure on that point. So we want to prove that this converges in the weak star topology to the Dirac measure on P0. Okay, so this is the definition of physical measure. So we are proving in this second case, we are proving that P0, the Dirac measure at P0 is the physical measure for the system. So we want to prove that this sequence of measures for any P, and this has total Lebesgue measure in the solid torus. So for any P in this set, this accumulates in weak star topology in the Dirac measure of P0. And this is given in this simple lemma. So any weak, so what we actually are going to prove is that any weak star accumulation point is delta P0. Well, if any weak star accumulation point of a certain sequence is a certain measure, then necessarily it converges to that measure. See that any sequence here has accumulation points in weak star topology. Okay, so the proof is very simple. So assume that it converges to a certain measure, and since the push forward is continuous, we have that the push forward of this sequence converges to the push forward of the accumulating the measure it is accumulating. So using, well, the push forwards are linear, and using, so 34 is this fact that it pi semi-conjugates, we can see that, so this is so the measure, the sequence is defined here. So I'm applying pi star, so I can take pi star inside. But then I can see that pi star of this is by the semi-conjugacy is pi of the image. So this is the semi-conjugacy. It's very easy to see this property. But and then this is equal. Sorry, here is not the semi-conjugacy. So here is a simple feature of push forwards and Dirac measure. The semi-conjugacy is used in the next step. So in the next step, we obtain that this is true. So the sequence of push forwards is this sequence here. Well, and we know that pi of p belongs in B. And so this sequence is converging to delta 0. And so we obtain that easily that necessarily mu has to be equal to delta of P0. Here we also use that in the fixed disk, every point converges to the fixed point. And so we obtain this. Okay, so the interesting case is when alpha is between 0 and 1. Well, in this case, the situation is much more delicate than in the circle map. In the circle map, we have constructed that natural partition, which appears here. The natural partition was, so we induced, in that case, we induced for the circle map, we induced first we use the first inducing map, and then we use a second, which I did not explain how to obtain, but we obtain a second induced map. And the second one could be obtained, well, I told that it could be obtained in J1, but actually it can be obtained in any union of the J's here. It's not difficult to see that part. I told J1, but if you go to the slides, I improved it a bit to convince you that it can be obtained in any union. So I'm going to consider a union of two J's. And you may ask me why union of two J's and not just one and not just J1. Well, union of two is to be sure that when I induce, the greatest common divisor of the inducing times is 1. Because the inducing times, well, according to the way we have created the induced map for F, which I called it Fs, it is related to the returns to well, now to Jn0 union Jn0 plus 1. And see that for that, we first consider the iterates for which it escapes from this region, and then we consider the returns. And these points escape, so in Jn0 escape 1 unit less than in Jn0 plus 1. And so this makes that there will be points with consecutive return times. And so the induced time, the greatest common divisor has to be 1. So this is the only reason. The other reason to obtain not in J1 and one of these is that I want to induce in a very small region. So if n is very large, this will be very small because these j's are accumulating in 0. And so, so we have an induced map, Fs. And so there is a natural partition. I call it Q. And I'll list the elements is a countable partition associated to the induced maps, which is a Gibbs Markov map. And I call them omega 1, omega 2, and so on. And associated to this omega, see that the omegas, they are in S1. So now look at this second picture. So the omegas, they are in S1. So we can consider the points. So associated to, for instance, this little omega 1, I will create the omega 1. What is that? It's the set of points that are in the attractor, the solenoid attractor, and project into it. So the solenoid, there are lines here. See, here I draw them no curvature, but they have some curvature, and there are lines here. And so I consider the elements in the attractor that project down to the element in the partition. And so I'm creating a partition in a certain region of the solenoid. And this omega i's will be used to construct a set with a Young structure here in the union of the omega i's. Well, we can prove this this example, this is the advantage of this example, is easy to manipulate and make some calculations, and we can prove that there is an invariant cone. Well, according to the expression I've presented, the cone is this one here. Well, it's not so important, the expression. The only important thing is that for every point in the attractor, we have a cone which is invariant under the dynamics, and the angle converges to 0. See, this is clear in uniformly hyperbolic context. Here we have a point with derivative 1, but still we have this conclusion. And moreover, I cannot assure that I have expansion, uniform expansion, but I can tell you that I have this, at least this bound on derivative for points in the cone. And also when I return, yes, I have expansion for points in the cone. Okay, so this is the idea that when I return, I have a uniformly expanding map. Now, see that F now is the solenoid map. Okay, so using this, we obtain partially hyperbolicity, because we also have a uniformly contracting direction, is the direction of the disks. And since we have see that for contraction in the disks, we have this contraction in the disks. So that's why I've taken in the disks, I take a somewhat strong contraction to compensate. So this is the best we could achieve in these calculations. So this contraction is stronger than any possible contraction in this direction. So the fact that we have the cones and the slopes go to 0 makes it possible to obtain an invariant splitting. And then in the invariant splitting, this is the estimate that we had in the cone, this V/4. And so this contraction is stronger than any possible contraction here. And so this is an invariant splitting, dominated the composition, and with a strong conclusion, a strong contraction in the other direction. This is what we call a partially hyperbolic set. Well, partially hyperbolic set, there's a classical result by Schub, which says that there is center unstable disks tangent to this center unstable direction. And they are invariant in this sense. So at least the part, this is the ball, B epsilon is the ball. So at least the part of so a neighborhood of the disk, that's what it says, is sent into the disk in the image. And also, and this is why I'm mentioning this result, is that these disks, they depend continuously in the C1 topology, they depend continuously on the point. At some point, I need this dependence of certain family of disks I'm going to consider, and so this is the way I can assure that they depend continuously on the points. So, well, these disks are not necessarily unique. This family of disks is not necessarily unique by the result of Schub, and there's nothing that assures that we have expansion. So we only have expansion in the return. So this will be enough to prove that the measure nu, this is the measure we have in the dynamics in the circle. So the measure nu can be lifted to a measure so the measure in the circle can be lifted to a measure in the solid torus. This is essentially using a Bowen argument of lifting measures for extensions. And this measure has the support of that measure coincides with the whole attractor. And we can prove that that measure has a positive Lyapunov exponent in the center unstable direction. So if it has a positive Lyapunov, so the positive Lyapunov exponent is because it projects down to the measure, which is the good measure in the circle, and in the circle we have a positive Lyapunov exponent, so we can manage to prove it has a positive Lyapunov exponent above. And so with that, we have local and stable disks. And we can prove that the local and stable disk is contained in this, which are also disks obtained by Schub. These disks, as I said, obtained by Schub is essentially to assure that these local and stable disks, they also depend continuously. So we have these local and stable disks, and so using these disks, I will be able to construct a Young structure. So how do we do that? Well, the family of stable disks will be easy. So is the disks that we have in the solid torus contracting uniformly. So we need to construct a structure as the one I mentioned in the beginning of this lecture. I need to build a family which I call gamma U of unstable disks, and such that we obtain in the intersection of the unstable disks with the stable disk that we have, we obtain a set with a Young structure. First, we take n sufficiently large such that the projection of this unstable, it's a center unstable disk by Schub, contains this element here. And there is an unstable disk. So what I want to prove is that there is there is an unstable disk of Pezin that projects to this region here. That's what I want. Okay. And the idea, I'm not going to follow this explanation. The idea is that in the base dynamics, so this disk contains a center unstable disk, and then it projects down to this interval here. This interval here, necessarily, it expands in the base dynamic because the base dynamic is strongly expanding. So at a certain moment, it becomes everything. So when we reproduce that above, it tells us that any disk I take, so any unstable disk I take, grows to a scale of order I0. So I0 is when I project down, okay? When I project down, is order of I0. So this is the idea of this line. And so this is a disk. So we have a disk in the solenoid, such that the projection by this is the vertical projection pi is a good region for the base dynamics. So it's the region where we induce in the base dynamics. And so I will use this disk. This will be, so as I said, there will be an inductive construction to build the set of unstable leaves. The inductive construction starts, so there will be a certain sequence of gamma n's, and the very first is precisely made by this gamma 0. And how do we obtain assuming we have one constructed, how do we obtain the next one? Well, let's look at the first step. In the first step, so I have this gamma 0, and recall that I have, so gamma 0 projects down to I0. In I0, I have the partition in two elements, omega I, omega 1, omega 2, the little omegas. And the pi minus 1 of this, when I intersect with the solenoid, pi minus 1 of these little omegas give rise to the big omegas. And so I have a partition here on this set, which is I0 times the solid, well, it's the part, it's not the solid torus, it's the part in the attractor that projects down to I0. And so I have a natural partition, in particular in this gamma 0, is the intersection of the capital lambdas, omegas, with the leaf gamma 0. And I know that down the corresponding part in the corresponding, so associated to omega 1, I have a time, S1 is the return time. So the corresponding dynamics down sends the little omega 1 to the whole I0. So it means above that the corresponding part here intersecting gamma 0 in S1 iterates comes to a disk that projects down to I0, okay? And so this will be another element in the family of unstable disks. See, this is in some sense a minimal construction, because if we want to have the Young structure with the same inducing times, with the same recurrence times that we had before for the base dynamics, the image under S1 of this first element here, which is this new disk here, necessarily needs to be there. This is one of the requirements of the Young structure. And so we have this first one. And we need, for the other ones, the other image disks, okay? And so that's the way from gamma 0, I obtain gamma 1. So considering the partition on the leaf gamma 0, the natural partition induced by the partition in the base dynamics, and then considering the respective images of those elements that I obtain in gamma 0. And so I obtain the new leaves. And well, we proceed inductively, and this is the way that we describe the next steps. And then we consider the union of all these leaves. The problem is that the union may not be a compact set. So, and the union of all these disks is here, okay, in the elements that we construct in this way, and then we take the closure. The problem is that we have disks, but when we pass to the closure, we want the compact set lambda to be foliated by stable and unstable disks in the Young structure. Through each point, and must pass a certain unstable disk and unstable disk with certain properties. So taking closure can be a problem. Well, it's not a problem. In fact, we can prove that through any accumulation point, that's an explanation here, but I'm not going to read this. Through any accumulation point, we have an unstable disk passing through it, and the unstable disk is still contained in lambda. See that in this way we obtain a full Young structure. So the unstable disks that define the Young structure, they are contained in the Young structure. And so that's the way we build this set with the Young structure. And then we consider the stable family is the obvious one. So you consider the disks transverse to a certain point in the circle, and these are the stable disks. And so this is the last slide. In this way, we can prove that it has a Young structure. So most properties come from what we know already from the base dynamics. And so many the properties, some of them come from there, the geometric ones at least. And then we can prove that it has a full Young structure with recurrence time the same of the base dynamics. And according to the choice of the recurrence times, the greatest common divisor will be 1. And the estimates I think here there's 1 unit less. So it's 1 over alpha minus 1. So, oh, sorry, here is not the decay of correlation. No, this is correct. So this is the tail of the recurrence times. So the tail of the recurrence times is this, and for the decay of correlations, we lose 1 unit. Okay, so with this, and that's what it is here. So the decay of correlations, we lose 1 unit. So the measure, the support coincides with the attractor by a proposition I've presented you before, and so it coincides that the solenoid attractor is still transitive as the classical one, and almost every point belongs in the basin. Well, there's an explanation here. I'm not going to read it. Well, this is because in the base dynamics, almost every point belongs in the basin of the measure. It's lifted, so we can use this argument to prove that. Almost every point belongs in the basin. So that's all for today. So in the next day, I'm going to give you some ideas of applications to non-uniformly expanding maps, endomorphism case, and partially hyperbolic systems, the diffeomorphism case. Okay, thank you very much. Any questions?
Yes, can I ask a question?
Yes, please.
So, would it be possible to to do these arguments for a different class of measures instead of the Lebesgue measure?
Yeah, that's well, it's related to the question of Lucas last day. Yes, provided you need to consider conformal measures, but then you obtain partitions which are related to the measures. So the partitions in all these, they are, in this case, Lebesgue mode 0 partitions. Let me say that Wilton has some results with, I still haven't seen an adaptation of the results in the endomorphism case to the diffeomorphism case. But there are some results where, in some sense, you obtain some universal partitions. And I guess using that, we could obtain something for at least conformal measures. I guess so. I didn't check details. Actually, I didn't try to check the details, but I believe that something can be done in that direction.
Yeah, I'm asking because yesterday he mentioned that in the workshop next week, he'll talk exactly about these induced systems to prove the uniqueness of the measure of maximum entropy for Viana map.
Maybe he will use those results. I haven't talked to Wilton for a long time. We haven't updated the novelties. So maybe that will be good if he talks about that. I believe it can be done. At some point, we had the idea of adapting, but there's no time available for all ideas we have. Okay.
José?
Yes, Lucas.
Yes. So,
okay.
I
mentioned you.
Sorry?
I mentioned you.
Oh, okay, yes, I was here listening. But, okay, so at some point I got confused, and I think the confusion.
I'm sorry.
It's right in the beginning because these leaves that we have over there.
Let me go to the beginning. So the beginning of today.
Yes, of today. Yes.
Let's see. You should have told me that in the beginning.
No, but I realized I was confused just later.
Where
but,
here? Where?
No. So my question is something like this: this local structure that you have here, sorry, this product structure that you have here.
Yes.
It's not clear for me if it's given locally at each point in lambda.
It's global in lambda.
Oh.
So lambda is intersections of these points. So there's a family of stable disks and a family of unstable disks with these properties. So this is usually a small region.
Okay, so these leaves, they can be dense in M, for example, or if...
Well, what happens if you, for instance, iterate forward these little unstable disks? They may be dense in M. It depends on what is the dynamics out of this region. Yes, it may happen.
Okay, but if we
these are local stable and local unstable disks.
Okay, so they're local. So
yeah.
Then I got confused in the picture of the induced map where you collapse you take the quotient map.
Yes,
because
maybe the picture is not.
It can happen that the image is very far away from the original gamma zero.
Here, this picture.
Yes.
What?
It can happen that this image is very far away. I mean, it's still a return, so it's in lambda, but it can be far away, even though from gamma zero, right? So there is no allonomy.
Yes, it's in one of the is in one of the blue disks in the previous picture. So FR of X is in one of the blue disks. Yeah, it can be far away. Why that? Why not?
But there is no allonomy to project back to gamma zero then?
No, it's a point still in lambda. So if it's still in lambda, there is a point through stable leaf through it and an unstable leaf through it.
Yes, but the stable leaf through it, it's necessarily passing through gamma zero.
Yes.
Okay.
Yes. The picture is exactly this one. So lambda is the intersection points here. Is a full product. So a product.
So it's global in some sense, not.
Is global in this local structure? Yes.
Okay. Okay.
It's a global product in lambda. Lambda is very small, but it's a global product.
Okay. 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 Now I get it.
So when you take a point here, it comes to some other point here on which there is a stable disk and an unstable disk. So you can project down. I'm not going to do, but imagine you take this gamma 0 as this very first one here, and it comes here, so you can project down here.
Okay. Okay. So yeah, now it's clear. Okay. Thanks.
It's clear now?
Yeah, it's better. Thanks.
And see that, so each, maybe I didn't give a sufficient highlight to this property here. So each stable disk intersects an unstable disk and in exactly one point. Okay?
Mm-hmm.
So this is not, this is in the product structure for hyperbolic set. This doesn't happen globally in the hyperbolic, so this is just local product structure. Here, if you think of lambda as our hyperbolic set, then this is a global product structure, but in lambda, which is a local set. Well, I hope you understand. Okay, so it's global in lambda.
Yeah. That's it. It answers my question.
Okay, so that's why we can make a global quotient. But otherwise, we will have problems. Okay, any more questions? Okay, so you have the notes available in this link. Okay, so if there are no more questions, see you on Friday.
Thank you, Zé.
Thank you, Zé. See you. Bye-bye.
Thank you.
Welcome.